Okay, hi there, Dr. Matthew J. Traum here. This is the second video in the derivation for the failure pressure for the O-rings in our stopcock, in our Buret stopcock combination. I did the first half of the derivation live in class and recorded it, so you should be able to see the first video there. And then the second video I'm kind of recording asynchronously so that we can continue and get to the end so that you have the whole derivation in combination with the notes to see how I did this. And again, this is meant to be an example of the type of analysis that we'd like to see for Mech 1 style analyses, so failure type analyses in the reverse engineering report. Of course, we're doing the analysis on an O-ring on our stopcock here, which sits inside a Buret, which fits over and these O-rings seal. Okay, and the point where I got to when I stopped the last lecture was effectively here, and we had written the Hertz contact equation for the pressure in this contact space between a small cylinder and a big cylinder, and I had explained what R star was, which basically if I blow this guy up, this R2, and make it effectively infinitely big, right? So if I draw a cylinder that's infinitely big, the radius is way down here somewhere, and it comes up like that, and that R2 is very big, and so this curvature, as R2 gets bigger and bigger and bigger, this curvature becomes closer and closer and closer to just being flat, and that's ultimately what we want, right? We effectively want a cylindrical surface being squished against a flat surface, or cylindrical O-ring being squished against a flat surface, and so that's how we're able to modify the Hertzian contact radius here to get it to be representative of just a cylinder and O-ring on a flat surface, which is what we want. So I got that far, that R star equals R1 for cylinder on a flat surface, and now I need to continue with trying to figure out what R star is. And of course R star, this is just given to us. I made a joke at the end of the last class that this is the law of conservation of chalk. I'm not writing in chalk, I'm writing in pencil, but the joke is the same, in that I'm trying to just reduce the amount of stuff that I write when I'm writing this equation. So R star is also effectively just a modified Young's modulus, and it has the same units, and so to get to R star, I need the following equation. So it's 1 over R star, and that's going to equal 1 minus Poisson's ratio of the first cylinder squared divided by E1, and then we're going to add to that 1 minus the Poisson's ratio of the second cylinder squared over E2, and these are things that I can look up, right? So if my O-ring is rubber, some sort of silicon rubber, I can look up the Young's modulus and the Poisson ratio for that. And then if the Buret, which I don't have here, but the Buret we believe is made out of acrylic, so I can look up the Young's modulus and Poisson ratio for that. I can plug those values in, and I can solve for E star, and then that E star value fits into the pressure equation by getting plugged in right there, right? So the whole point of this is to run through and convert a number of things from this expression for the seal to function correctly that I don't know, right? I don't know, things about the force, and I don't know things about the pressure, so I'm going to try to, put those pieces in to get an expression here that gives me finally the value of the pressure in that space, which will tell me whether the O-ring is sealed or not. So this is just something that I can now stick in for E star that I now know. Okay, so having come up with that, and this it's just just from the Hertzian contact equation, right? I'm just really trying to save space by writing this big thing more compactly in that more simplified equation. Now I can move on to the next topic, or the next concept here, which is I'm trying again to get things that I know into this equation, and so I need to come up with some sort of relationship that's got the pressure in it, or that's got the force in it somehow, so I can flesh this guy out. And so what I'm going to do is I'm going to go back to Hertzian contact. Ooh, no, not Hertzian contact, but my Hooke's law. So let me show you guys. Okay, so here we go. Right, so here's Hooke's law. And the Hooke's law analogy is this idea that if I start out with an uncompressed O-ring, and I imagine that it's like a spring, and then I compress it with some force, it's going to compress by a distance d, lowercase d. And so that compressed spring is very similar to a compressed O-ring, and that it still requires a force to compress it, and it's going to compress by a distance of lowercase d. So Hooke's law, we know it for a spring is this guy, but you guys also should know it from mechanics of materials, expressed in this way. So it's going to be the stress is equal to the Young's modulus multiplied by the strain, and the strain is just the deformation under some stress in the numerator, and then in the denominator we've got the unstressed characteristic length. So you guys might remember this from mechanics of materials as something like delta L over L naught or something like that. So that's the mechanics of materials way that you might have seen this. But I'm just going to leave it sort of as words here, because we're not really dealing with delta L over L naught. We're dealing with a different combination of variables, because we have a toroidal shape as opposed to just a shaft or a rod or something like that we're deforming. Okay, so that's the strain, and then so let me just write that strain, and then what's the stress? Well, that's the sigma thing, and stress is just a pressure, right? It's got units of pressure, so it's the amount of force that's acting over some cross-sectional area inside whatever it is that the object is that you're putting under load, and it's actually this force that we want, right? So if I go all the way back here, this force, that's effectively the force that we're talking about, right? Because that's the force that's causing this compression that we're using to facilitate the seal. So this is pretty promising. That I probably should be able to use Hooke's law to get to a useful result for my Hertzian contact pressure. Okay, and before I forget, let me just remember here, with this Hertzian contact pressure equation, let me put it in a big circle so that I can find it again, and I'm going to refer to it as equation number 1. So that's my equation 1, and then just for like completeness, I'm going to circle this guy, my E star equation, and I'm going to call this equation number 2, and you can start to see how this is going to work. I'm going to start with equation 1, and then I'm going to build up other equations, equation 2, equation 3 from Hertz's law, not Hertz's law, from Hooke's law, for F, and I'm going to just build up this series of equations, and then I'm just going to plug them all back into each other in the end, and I'm going to get the expression that I need for that sealing pressure. Okay, so how then do I figure out, if I'm interested in kind of quantifying in some way this stress? I need to figure out an expression for the force, and I need to figure out an expression for the area. And so if you remember back to kind of our original discussion about what the O-ring does is it deforms, it's this contact area multiplied by the circumference of the inner axis of the O-ring that gives us the total contact area. So I need really to figure out what this lowercase a is to get to this area, to be able to plug it into this equation, to get an equation number 3 that I can stick in here and solve equation number 1 for a relationship between pressure and force. So I'm going to need some clever math to do that. And so what I'll do is I'll just draw the geometry again. So here's my cross section of my O-ring, and of course it sort of shoots off into perspective there. And this is the center line of the O-ring, right? So if I actually look at my O-rings, this center line represents a line, through the center axis of the O-ring, right? So I'm looking at the O-ring, kind of like that, and I'm cutting it and I'm looking at it. So that's just maybe a section cut of the O-ring. And I've got a couple of dimensions, and these are dimensions that I can measure, right? This is the key thing, is right now the equation is in terms of a bunch of things that I really can't measure and I can't quantify. And so I want to come up with a version of the expression that has things that I can measure. And so one of the things that I can measure is the radius of the O-ring. So from the center line here to the center of the O-ring, and I'm going to call that capital R. And then another thing that I can measure is the radius of the cross section of the O-ring itself. So I'll call this R1, and this guy, of course, is just the center point. So capital R goes from that center line that I described before to the axial center. Right here's the axial center of the O-ring, and then R1 goes from the axial center of the cross section of the O-ring out to the outer diameter of the O-ring. The other thing that I want to put in this drawing is the Buret wall, right? So if the Buret wall comes in here, and I'm making sure that the Buret wall interferes with the O-ring, right? Because it actually compresses the O-ring, and so we need to make sure that we've got interference there. The inside wall of the Buret, if the Buret's inner diameter is d, then the distance from this center line to the inside wall of the Buret is capital D over 2. So let's just label this Buret wall. Okay, and just for clarity, this is O-ring. Okay, now I've got to do some kind of nifty geometry here. So I'm going to attempt to freehand draw a circle. Wish me luck. Okay, not too bad. And then here's the center of that circle, and then on one side is going to be this Buret wall, right? So here's the Buret wall. Buret wall, and then on the other side is going to be the stopcock wall. So here's the stopcock wall. Okay, and this is just I'm sort of taking this and I'm just zooming it outwards, right? So just think of this as like a zoom. Woohoo! Okay, now because I've got this O-ring compressed between these two solid surfaces, the stopcock and the Buret, it's going to deform, as we've already talked about. So I'm going to draw it sort of deformed like this, and deformed like this on the other side. Okay, and so here's now just the normal O-ring, and then here's the deformed O-ring. Okay, and I can extract from this picture some geometry that will help me to figure out what this contact surface is, right? This is really what I'm after, is what is the area of that contact surface between the deformed O-ring and the Buret wall, because that's the area across which this deformation force is acting, that causes the pressure in this space that prevents the fluid from leaking through. So I'm gonna just take now half of this guy. So here's half of it, and I'm gonna draw again just a half circle. So wish me luck with that half circle. Ooh, okay, there we go. So there's my half circle, and then I'm gonna draw like half of this deformed O-ring. half of the deformed O-ring. Okay, and I need my eraser because this is a terrible drawing. So let's just erase some of the things that we don't need, some of the superfluous things. Bing. Okay, great. Here's still that center point, and you know, all I've done is just taken this image and I've cut it in half, and I'm just drawing half of it, and that's really just you know, to clarify and simplify the geometry a bit. Okay, so from over here, I know that the radius of the O-ring from this spot to the edge is capital R1. It turns out that I also know, right, because this is a circle, that the distance from this spot to this spot here, which is effectively where the compressed O-ring, where the end of the point where it's in contact with the Buret Wall, right? Because remember, the Buret Wall is right here, right? So that contact point, that's sort of the end of the contact point. That distance is also R1, right? And it doesn't seem like it, probably because my drawing is not great. But these are two radii on the same circle, right? So if I start from the center and draw them outwards, they have to be the same distance. And so you could start to see the beginnings of a triangle that I can construct here. If I'm interested in this total distance, that total distance, half of that distance is A, and double that distance is 2A. So if I go back to this drawing, you can see here, I kind of knew where I was going with this, and I set this as you know, A from the center line to one edge of contact and A from the center line to the other edge of contact. Those A's are the same A's that I'm drawing here in my attempt to construct this triangle. The last piece of information I need is you know, what is this distance here? Because ultimately, when I blow up this triangle, this is what it's going to look like. So we're going to go with Pythagorean Theorem. Pythagorean Theorem. Okay, and I've got one leg of my triangle, which is going to be distance A. I've got the hypotenuse of my triangle, which is going to be distance R1, the radius of the uncompressed O-ring. And then I need a third side here, right? And this is going to be a right angle, because this, of course, is a right angle, because I'm just capitalizing on symmetry, top and bottom symmetry. So what is this distance? Well, if I look back over here, the distance all the way out to this edge is well, it's R plus R1. So I'm going to just describe like this little section of it here. I'm going to describe this section of it as D, and what we'll just call that lowercase d. And what that means is that if I start here at this O-ring center line and I go just to that location, that means I've traveled the distance R1 minus D, lowercase d, R1 minus D, right? So this is just R1 minus lowercase d. And we'll see in a second kind of what that is, but for right now we'll just leave it there. Now I could do Pythagorean theorem on this, right? So I know if I say R1 minus D squared, so that's this leg, plus A squared, that's this leg, that has to equal R1 squared, that's the hypotenuse, right? So that's just Pythagorean theorem. I'm now going to carry through with this this square symbol here. So this is going to be R1 squared minus 2R1D, and then plus D squared plus A squared equals R1, right? So that's just me carrying out that square symbol. I've got R1 on both sides of this equation, so that R1 and that R1 are going to cancel with one another. And so what I'm left with then is just A squared is equal to, let's see, A squared is equal to D squared. Hang on. I gotta think about this for a second, minus d squared plus 2r1d. Right, so all I've done is just leave this guy on this side and move everything else to the other side of the equation. So that's where this little negative sign comes from. Of course, it doesn't really matter all that much because I'm going to make another kind of engineering simplifying assumption, which is I'm going to say that d is small. And what that means is that really from sort of an engineering perspective is that R1 is much, much less than D. And if you really think about it, right, I didn't draw it particularly well, right? R looks like kind of a pretty big percentage of D here, but this is an O-ring, right? It's a little bit squishy, but it's not like so compressible that it's going to deform by 50% of its size when we compress it. The compression is relatively small, and so this D is maybe like 2%, 3% at the most of the total R1. And so this is relatively true, right? This guy is about an order of magnitude, maybe 2 bigger than this guy, and I'm going to make this situation even bigger, right? So I'm going to, instead of just saying R is much greater than D, I'm going to say 2R1 is much greater than D, and then I'm going to go one step further. I'm going to say 2R1D is much greater than D squared, right? So I'm just here multiplying by 2, and then here I'm multiplying both sides by D to get to this guy. And if I get to here, I can now compare this term, which is 2R1D, right, which is right here, to D squared, which is here. And if 2R1D is much bigger than D squared, then voila, when I compare these two terms together, this guy goes away just because it's small. And I'm left with just that A squared is equal to 2R1D. And ultimately then A is equal to 2R1D square root. Okay, so that's pretty good, right? So I'm almost there. I'm again trying to find values that I can measure, plug into things that I don't know to get to what this contact area is between the O-ring and the burette. R1 is very easy to measure. D, not so much, not directly, and so I need a better way of writing D. Okay, so what is D? Well, if I go back to this original drawing here, what is D? D is the distance from, make sure I got it here, right. So it's the distance from the center all the way out to the end, and then like compressed by a little bit. So if I'm going to rewrite it, I'm gonna rewrite it this way. So let me switch pages here. So it's actually now going to be lowercase d, this thing that I don't know, which again is just the amount of deformation in the O-ring, is going to be capital R plus R1, and then minus the inside diameter, the inside radius of the burette. So that's what that is. And now if I plug this guy into my previous expression for A, I'm going to have that A is equal to 2R1 times lowercase d. And what's lowercase d? Well, it's this big thing. It's R plus R1 minus capital D over 2. And I'm going to take the square root. And there we go. So that's now my value for A in terms of all things that I can measure, right? I can measure the diameter or the radius of the O-ring itself. I can measure the radius of the O-ring from the center of the O-ring out to the center axis of the O-ring. Here's R1 again, which I can already measure. And then here's D, which is just the diameter of the burette, which I can also measure. And so I'm going to put this guy in a box, and I'm going to call him number 3. Okay, let's see. Number 3. Does that make sense? Yes, right, because I've got equation 1 here, I've got equation 2 here, and now I've got equation number 3 here. Okay, so I've got all those pieces kind of now arranged, and so now I need to come up with the strain. So remember again, the strain is the CL deformation divided by an unstressed characteristic length Okay, and of course the reason that I need the strain is because I'm trying to use Hooke's law, and I now have an expression for this area, right? I can come up with that because I know A. I know the Young's modulus. I can look that up for my rubber O-ring, and so I'm looking for this guy, right? So that's the strain, and if I know the strain and I know Young's modulus and I know A, I can put all those pieces together and I can get an expression for F that I can then stick in to my Hertzian expression here. I know everything else, and I can solve for that pressure. Okay. Whew. So what are these values? Well, the CL deformation we've already said is just lowercase d. So that's from here, right? So this guy is just deformed by an amount d. So that I've already defined. And then what is the undeformed O-ring characteristic length? I am going to use R plus R1. So that is, let's see, that's the length from the center line to the center of the O-ring, central axis to the edge of the O-ring. It's going to be my non-deformed O-ring length. And this guy is now going to equal, well, I have an expression for D, right? It's R plus R1 minus D over 2 divided by R plus R1. Okay, so there we go. We've got that. And I can now plug that value in to my strain equation, my stress strain equation, my Hooke's law, to come up with a relationship between all the things that I need to know. All right, so let's do that. So here's my Hooke's law equation again. And if I rewrite this, well, this term is just the force over the area. So let's say sigma is equal to force over area. What is that? Well, okay, it's a force, which I'm still trying to find, over the area. The area is 2A L, right? Where again, A is that lowercase a, that contact area. L is the circumference of the O-ring, and we have an expression for A, right? So it's just let's see here. It's just, now I've lost it. Give me one moment. All right, we'll come back to that. I have an expression for A, but I've kind of mixed it in with my papers here. So we'll leave it right there for right now. I'll be able to come up with this in a second because I've got it written down later on in my notes. So there's that guy, and then I need the strain, right? So this is going to be now equal to the Young's modulus times the strain, and here's my strain expression: R plus R1 minus D over 2 over R plus R1. Right, there we go. Okay, so with the exception of my inability to find A, which I've got it written down somewhere, I just don't have it off the top of my head. That's the expression that relates all of these things that I now can measure to the force. So I can take that force and I could stick it into my Hertz equation. So when I write this all out, this is going to equal E. So there's E multiplied by capital R plus R1 minus D over 2 divided by R plus R times 2L times 2R1 and then multiplied by R plus R1 minus D over 2. And let me put this in parentheses. And then this is going to be raised to the 1/2 power, and then I need an appropriate closing parentheses there. Okay, so that's the expression that I should ultimately get when I plug in. Right, this guy is here, and then this is all of the stuff that I had written down for A, right? So like this is, oh, here's the A expression right there. That's why I couldn't find it, because it's on the same piece of paper. Hallelujah, there it is. Okay, and I should also be really clear about this, that this L and this L are the same L. And let me just be really clear when I go through. Okay, so I'm going to use capital L, and that's because I use it here in my Poisson in my Hertz equation. Okay, so I'm just going to call this capital L. It's again the circumference of the O-ring. Okay, almost there. Now I'm going to put this guy in a box. I'm going to call him number 4. And I'm going to now plug number 4 into number 1. And remember, number 1 is just my Hertz equation. And so let's do that. So I'm going to have my pressure is going to equal E star, which I know how to calculate, multiplied by force. Here's my equation for force. It's E R plus R1 minus D over 2 divided by R plus R1 to L. I'm just copying the previous line. R1 multiplied by R plus R1 minus D over 2 1/2. Okay, right, I've got this all copied down. Okay, and now it's going to be divided by, right, because we're going back here, divided by pi L R star. But what's R star? R star is just R1. We figured that out before, so R1. And now, and I have to put the whole thing in brackets and take it all to the 1/2 power. There is one sort of nice cancellation here, which is that L and L cancel with each other, so that tells you that it doesn't matter how big the O-ring is, right? What the circumference of the O-ring is doesn't matter for whether it can seal or not. And we're left with kind of the final version of the expression, which I will clean up and simplify by using some algebra. So here it comes. That pressure is equal to 2 to the 3/2 multiplied by E. That's the Young's modulus of the silicone rubber, multiplied by E star. That's the modified Young's modulus of the silicone rubber plus the Buret acrylic surface. And then here comes my geometric terms. And this all gets raised to the 3/2 power. Again, I'm skipping a number of algebraic steps and leave it up to you guys to run through those. Pi R1 to the 1/2, and then this gets multiplied by R plus R1. Okay, and I'm going to raise this whole thing to the 1/2 power. And there you have it. So that took some doing, for sure. It wasn't easy. but now we have it. So in the notes, I think I wrote, wow, wow. And why wow? Because this is now an expression for that sealing pressure for the Buret stopcock O-ring in terms of all things that we can either look up or measure, right? It's all in terms of geometry and material properties that we can look up and measure. In the notes, I go through and I do what I call a sanity check. It's always good when you go through a really complicated derivation like this to convince yourself that it's right by just checking the units. So I do go through the units, and I'll just do it quickly here. So the units of E, Young's modulus is pascals. We've got 2 of those. The units of this guy are all going to be a length. And that length is going to be raised to the 3/2 power. And then in the denominator, I'm going to have a length raised to the 1/2 power, right? That's this guy, and then multiplied by another length. Okay, and the whole thing is raised to the 1/2 power. And so what happens when we go through all that? Well, this L to the 3/2 combines with this L and this L, and so those go away. And now we have Pascal times Pascal raised to the 1/2 power. And so this ultimately comes out to be units of pascals, which is what we want, right? Pascals is units of pressure, so that checks out. That's great. That means that it's a pretty good bet this is correct, because the units work out. Had we messed up and gotten something like pressure times length or pressure times something crazy, that would indicate a mistake. But that's the sanity check. So let's just write that here. Sanity check. Okay, success. So now we have this expression, and we can plug in for any O-ring the geometric values that we know, and we can plug in and back out what the leak pressure is going to be for that individual O-ring. Now, I do want to check this, to make sure that it's right. And I've shown you guys the syringe barrel from before. This was used in fall 2019. And in summer 2020 as the reverse engineering report artifact. I pointed out that there's a dynamic seal here, but there's effectively 2 O-rings, and so just to leave some modicum of mystery for you guys to look up, I did for the syringe determine all of the various values so that I could plug in, so that I could figure out what they were. So E1, which is for silicon rubber, is 2.5 times 10 to the 7th pascals, and Poisson's ratio for silicon rubber is 0.48, and those I looked up. And then for the syringe is made out of polypropylene. So E2 for polypropylene is 1.2 times 10 to the 9th pascals, and the Young's modulus for polypropylene is 0.42. So let's just kind of box these so they're separate. That's polypropylene. Okay, so those values, I can plug those in now to my E star expression. And when I plug them into my E star expression, it goes 1 minus 0. Oops. Sorry, hang on. I need 1 over E star. Let's try that again. Okay, 1 over E star. All right, and that equals, let's see, 1 minus the Poisson's ratio for silicon rubber squared divided by 2.5 times 10 to the 11th pascals plus 1 minus 0.42 squared over the Poisson's ratio. That is the Poisson's ratio. Young's modulus, 10 to the 9th Pascals, Young's modulus for, in this case, polypropylene. You guys will probably use acrylic here instead of polypropylene, but again, I solved this for the syringe and not the burette to leave something to your imagination. And so when I solve this, I end up with an E star of 3.18 times 10 to the 7th pascals. And does that make sense? Well, we're expecting to do somewhere between this value for silicon rubber and this value for polypropylene. And yeah, this is the value between those two. So that's fine. So that's the value that I come up with. And then when I take this E star and I plug it in, I need a few more things. So my diameter in this case, that's now the inner diameter of the syringe, right? So it's the inner diameter of the syringe barrel. So for me, that's going to be 0.01082 meters, and I measured that. And then R1, that's going to be 0.00089 meters. And then R capital is going to be 0.0053 meters. Again, those are all just from taking a caliper and measuring the dimensions of the O-ring on the plunger here, the silicone O-ring. And so when I take these values for D, R1 and capital R, and then for E star and E, and plug them into this expression, what do I get? Well, I get a pressure of about 90.7 atmospheres. So that is the leak pressure that I expect for the syringe. And I'll leave it again up to you guys to find the leak pressure for the O-ring so that something is left to for you guys to sort out. Now, I did a sanity check on this, right? We went through this entire big, cumbersome, horrible analysis. We got to the end. We got this number. Is this number right? Who knows? How do we find out? So what I did was go to the manufacturer, and I found the leak pressure for this syringe with the manufacturer. Guys, with the burette, once you identify what these O-rings are, you can do the same thing. You can go to like the Parker O-ring catalog, and you can actually calculate what the leak pressure of these particular O-rings should be based on their geometry, which you can measure, and their material, which you can, we can guess that it's silicone rubber, but you could actually do some testing and determine precisely what it is. But for the syringe, which is the one that I calculated, we were told from the manufacturer that the leak pressure is 102 atmospheres, which is pretty good, right? So this rough estimate that we did using a number of engineering approximations and assumptions got us about 91 atmospheres, and the actual value is about 102 atmospheres. So pretty good, pretty close agreement, at least for engineering purposes. And really the point of this is that this was a bounding analysis, right? So this pressure is lower than the actual leak pressure. And so barring any other information about the O-rings other than just doing this analysis, I would actually set the pressure, the leak pressure here, right? And of course with a factor of safety. But, I'd be pretty well convinced that if I don't have hydrostatic pressure at the Buret stopcock interface that exceeds this value, that it's not going to leak. It is a lower bound because the actual value is a little bit higher. Okay, so that is the derivation. It was a little bit of a bear, but I wanted to walk through it to just give you guys, a sense of a Mech 1 type failure analysis for a seal, which is probably not something that you've seen before in your lower division or upper division mechanical engineering courses. Just kind of wanted to walk you through how it worked and give you a sense of what the numbers are. So with that, I will wrap up the derivation. Thanks for your time and attention, and look forward to seeing you guys in class. Thanks. Bye.